Hello everyone and welcome to TLE Eliminators post-contest discussion for Leetcode Weekly Contest 472. Uh, we'll be discussing the problems from A to D today. And yeah, how was the contest? Before we get started, as usual, I like to tell you about TLE Eliminators self-paced courses. If you haven't checked them out, do check them out now. Our flagship courses are live right now. So if you're starting your competitive programming journey, or you're already begun doing CP, or you've begun practicing Leetcode, or doing DSA, and you feel like you're stuck, you feel like you're not improving, then you should definitely check out this course because even though obviously you have a lot of online and free resources, sometimes having a course which has some structure, which has which has videos every day, which has problems to solve every day, and which has a leaderboard does help you out a lot psychologically, right? As well as like a clear structured like problem, like you're not sure what topics to learn. So it does a clear structure. First you do level one, level two, level three, level four, and based on like what your current level is, you can choose what level you want, and based on what topics you want, you can choose what you want. So yeah, do check out the course. The course contains more than 40 hours of recorded lectures, more than 100 plus practice problems, hints and video solutions for all the problems, as well as doubt support by high-rated coders. And plus, all of this is being done like by top coders of India, right? So, and it's being for like super affordable prices. So yeah, definitely do check it out. All right. So, how was the contest? Let's see. 2 out of 4. Cool. I solved three. Interesting. A, B, C. C is C was pretty simple, I think. I'm not. Uh, yeah, C was quite easy. Yeah. Um, D was the only challenging question. For D, you would need segment trees, but A, B, C, I think was pretty simple. Just mostly implementation questions. Anyways, let's get right into the questions now. A and B, I guess most people solved, so we'll do those quickly. We'll spend more time on C and D. All right. The first question A. So smallest missing multiple of K. Given an integer array nums and an integer K, return the smallest positive multiple of K that is missing from nums. A multiple is any positive integer divisible by K. Nums goes up to 100 and K goes up to 100. So obviously the constraints are very small. You can write n squared solution and cubed solution, right? It doesn't really matter. But I will try to show you a neat and clean O of n solution, O of n log n solution, which I think is pretty elegant. Like if you want to implement this as a sub problem of some other problem, then I would say that's a pretty elegant solution. So problem A, right? And what we want is we want the smallest multiple of K that does not appear in nums, right? So we want the smallest multiple of K, smallest multiple of K that does not appear in nums. All right. So I'll just tell you the solution directly since it's mostly just implementation part. But so here's the idea. Idea is this: we're going to first sort nums, right? Sort numbers, sort our numbers. So sort nums, and then the second thing which we're going to do is we're basically going to set the missing value. So let's call the missing value, let's say missing is equal to K. Then for each then what we're going to do is for each element element x in nums, so in order, right? We sorted it, so we're going to go in ascending order. So for each element x, if it is equal to that missing value, right? If it is equal to that missing value, so if missing is equal to x, then we can do missing plus equal to k. All right. So basically, we're saying that if we have found the missing value, which was k initially, then we can increase it by k to the next multiple, right? And if we find the next multiple, then again we can increase it by k. And when this loop ends, it will have our answer. So we can just return this value, right? And so this solution is big O of n log n for sorting, big O of n log n for the sorting. Otherwise, it runs in big O of n. So let's just write the overall time complexity as big O of n log n, right? This clear for everyone. Here's the code. We sort the given vector, and then we initialize our answer to k. We say that the smallest missing multiple is k. Then when we go through all the x, if we find that value, we can say, okay, now the next smallest missing is x plus k, right? And then finally we can return the answer. That's it, right? Yeah, obviously you can do many ways. You can loop from k, you can you can do n square solution, n cube solution, there are many ways. But I think this is a very clean solution, and this kind of idea applies to a lot of DP problems also later on. All right, let's now move on to problem B. Longest balanced subarray. So this is also a very straightforward question. You just have to implement the statement. A subarray is called balanced if the number of distinct even numbers is equal to the number of distinct odd numbers. Return the length of longest balanced subarray, right? So distinct even numbers is equal to distinct odd numbers, and the length is only like 1000 or 1500, right? So what we can say here is basically, um, we can say problem B. So since the length is only big like 1000, right? So then big O of n squared solutions, right? Big O of n squared solutions will pass since it's only big O of since there's n is less than equal to 1500, right? So then if n squared solutions pass, that means that we can check all subarrays, right? So we simply check all subarrays, all subarrays. For all subarrays, you can just um, count distinct even numbers and odd numbers, right? And we can do this using set. We can do this using set or unordered set, whichever you want, right? We can just have a set for even numbers, set for odd numbers, and you can add elements to it. So use set or unordered set in C++, right? In your favorite language, you can use any kind of hash map which they have to keep track. And then we can simply find the max length one, right? Find the max length one. Find the max length one. Okay. So that's about it for this question, not just direct brute force implementation. I think it'll be more educational to look at the code instead of discussing it. So let's do exactly that. N is defined as the size of our array, and answer is set to 0 because initially we say that the length is 0, right? If there is nothing which is balanced, the length will be 0. Okay. Then we iterate over all the elements and we create this set odd and even. So this I is going to be your left point in your subarray, right? The I is going to be the left point in your subarray, and J is going to be the right point in your subarray, right? So first we iterate over all possible left points, then we create unordered set of odd numbers and even numbers. Then we can increase our right pointer. When we increase our right pointer, we can say that okay, if the number is odd, insert it into the odd set. Otherwise, if it's even, insert in the even set. Now, if the odd set and even set have the same size, then we can update the value of maximum answer, right? With this new length. And the length between subarray I to j will be j minus I plus 1. So that's why we update with j minus I plus 1 because that's the length of a subarray from I to j. Then finally, we can return our answer once it has taken max of all the possible cases. So it's a very direct brute force question. Brute force and STL is required for this, right? So time complexity for this is going to be big O of n squared, right? Direct brute force. I guess everyone would have gotten this, yeah? All right, let's now move on to C. Okay. To be honest, I will not put C more than 1200 on CF. So I'm not sure why people found that much difficulty with it, but okay. Let's move on to C. Lexicographically, smallest permutation greater than the target. You're given two strings, S and target, both having length n, which have lowercase characters. We have to return the smallest permutation of S, which is strictly greater than the target. Okay, so we're given two strings. One is S and one is the target. In my code, I'm just going to call them S and T. Fine, I'm going to call them S and T. And then we need to find the lexicographically smallest permutation that is strictly greater than the target. If no permutation is greater than the target, return an empty string. And Here's some definition like what lexicographic aggregator means. You should know that lexicographic aggregator just means which is bigger in dictionary order. All right. So permutation also they have defined. You should know that as well. And the length goes up to 300. So n cubed solutions are also possible. Although I believe my solution is like n square log n. But yeah, up to n cubed solutions are possible. Okay. So basically what we're saying is that problem C. So we are given a string S, right? We're given a string S. Let's say it's like hello, and we're given a string target, which is something like let's say LELHO, fine. And what we have to do is we have to find or maybe like let LELHZ or something. Fine. This is going to be our target. Now what we have to do, we have to find something which is lexicographically larger than this, right? So when we write characters out, as you see, E will be the first one, right? In the string S, E is going to be the smallest character, right? H will be the next smallest, and then L, uh, and then O, right? So if you sort S, then the smallest character is going to be E, then H, then L, then O, right? Yeah. So basically, we want to find. So just keep this in mind because the characters over here, the characters in S don't really matter since we're rearranging them anyways, right? The characters in S don't really matter. Can sort S if we want, or we can do whatever we want with S because they don't really matter, right? So, but basically, we just want to find something with the smallest one, which is lexicographically larger than this, right? Lexicographically larger than this. All right, and this can be done by using the following idea. So, what does lexicographically larger mean? So, let's just get into it. Let me just note down the expected time complexity. So, the expected time complexity for this is big O of n cubed. Okay. So, yeah, now let's get into the intuition. Okay. Intuition. Okay. So we need to understand what does it mean for a number for a string to be lexicographically larger. And basically lexicographically larger means that when we write the characters of the strings, right? When we write the characters of the string, so let these blank lines represent characters. Okay, like let these blank lines represent characters. And then we have a string S and we have a string T. So for S to be lexicographically larger than T, we need the first point of difference, right? First point of difference, point of difference between S and T, between S and T to be larger in S, okay? To be larger in S, all right? So basically what I'm saying is when you go character by character from left to right, so you consider this character first. It can have three options. It can be either S is greater than T at this position, S is equal to T at this position, or S is less than T at this position. So these are the three options we get at this given position, right? So if we consider that it's equal, let's say this was equal to C, this is also equal to C. So it's equal at this position. Then we can go on to the next position and we can check over here, right? And we can say that, okay, if this is equal to D and this is equal to A, then this will be greater, right? This will be greater. So we can say that this is lexicographically greater than T, right? S is lexicographically greater than T because at this point D is greater than A. Or what one more thing which can, let's say it matches here also. Let's say it matches here also. Then we can basically say, okay, we can take some lexo. If we have a larger character, then we can say that, okay, now it is lexicographically larger, right? And then since only the first point of difference matters, right? First point of difference matters. Um, we can already have one intuition. Okay, we can have an intuition. Since first point of difference matters, right? Point of difference matters. What we can say is that everything before this point was matching, right? Every character in S and T in S and T before this was matching, right? Then only this became the first point of difference. So every character in S and T before this point was equal, right? Was equal. And the second thing we can get is, um, and the second thing we can get is after this point, everything will be in sorted order. All right. So after this point of difference, after this first point of difference, first point of difference for the given question, for given question, we want the lexicographically minimal permutation, right? We want lexicographically smallest permutation, right? Or permutation of the string, right? Which is greater. So once we have a point of difference, right? Let's say our string S, was given as, let's say, AA, BB, C, C, D, E, okay? And our string T was given as CD, um, and let's say CD, A, B, B, C, D, A, something. Okay, this was our string T. So let's say that we rearrange S in such a way that their first point of difference becomes the third position. Okay, the first point of difference becomes the third position, and that's how we are rearranging S in a permutation. So when we rearrange S, what we want is that at this third position we have some larger value. So let's say this third position had a B, right? And then these two should be equal. So we will take this C and put it here, and take this D and put it here. So we got CDB, right? Now in all the remaining characters, so we used one B, we used one C, and one used the D. In all the remaining characters, they have to be put in sorted order. Okay, so they have to be put in sorted order. Since now B is already greater than A, so that means that this string which we have rearranged over here is already greater than T. So since we want lexicographically minimum, the remaining characters can be put as small as possible, or we can put them in sorted order, right? Because the next one will keep as small as possible, as small as possible, as small as possible. So then it will be lexicographically minimal. So what are the remaining characters? The remaining characters are A, B, C, E, right? So we'll put A, B, C, E as the remaining characters, right? So if the first point of difference was the third position, then we can put all the remaining characters here in sorted order. And the initial characters will have to be the same, because otherwise this won't be first point of difference, right? And then over here we can choose some value which is just greater than the value we have here. So we have A over here, we choose something which is just greater than A. Okay, so I hope you're understanding what exactly I'm trying to get at. Basically what I'm saying is that from the definition of lexicographically larger, we see that the main point which lexicographically larger changes is the first point of difference, right? The first position such that S becomes greater than T. So once let's say consider some first position, everything before that should be equal if this is your first point of difference. And since the problem wants the lexicographically smallest S, which is greater than target, then what we can do is we can make everything over here as small as possible for S, right? And then only this position will need to be greater than the target. So does that make sense, guys? Yeah. So are we going to have PCD of Meta Hacker Cup? Not sure. Probably we might have some recording. I think Abhinav might do that. Not completely sure about that. Yeah. Got the same intuition but couldn't implement code. That's fine. The code was a bit tricky. Yes, I can give that. Yeah. So let's try to make this like a compact algorithm. Okay. Let's try to make this a easy way so that you can implement it. This idea is fine, right? So the idea basically, let me first summarize the idea. So, okay. Summarize the idea. Summary. So what we can say is that the first point of difference, right? First point of difference between the final string which we have made. So we'll call that S dash. S dash means the rearrangement of S, right? So between S dash and T can be at I equals 0, I equals 1, so on until I equals n minus 1, correct? So let it be equal to I, right? Let it be equal to I. Then all S dash of j is equal to T of j for j less than I. Okay, for j less than I. So we're saying that when we pick a first point of difference, let's say first point of difference is 2, then for all j equals 0, 1, which is before 2, we should have exactly equal, right? So we will put CD like this. So exactly equal, right? And then the current position, the current position, which is equal to the current position is S of I, correct? S dash of I. So this position we will set in all these remaining numbers. So in all these remaining characters which are there, whichever is just larger in the remaining characters, in the remaining characters, remaining characters, we will choose the one just larger than, choose the one just larger than T of j, T of I. So that will ensure that the current character is greater than T of I, but it will ensure that we're choosing the smallest option as well, right? Since we want it to be lexicographically the smallest, so we're choosing the smallest option just larger than this position, right? So if this is the position of first difference, then we will choose the smallest value which can be larger than the position at this difference, right? And then the remaining values at this position. So remaining values can be filled in sorted order, right? In sorted order, right? And this gives us the solution for a first point of difference at I, right? This gives the solution for first point of difference at I. So we get a string, which is solution if first point of difference was at I. If first point of difference was I. So if we find for all I, we can take the lexicographically smallest for them, right? So find this for all I, find this for all I, right? For all I, and take smallest of them, and take smallest as the answer, right? As answer. By smallest, I mean the lexicographically smallest. Okay. So here some notes. Obviously, if we cannot do this, right? If there's not characters to match S dash of j equals T of j for j less than I, then obviously this will be not possible, and we can just continue, right? We can just continue this case. And also, if in the remaining characters there is no character larger than P of I, then again it's not possible, and we can continue here, right? If not possible, if this is not true, then we can just continue, right? If there's no character which is larger than the current position, then obviously it won't be able to become the first point of difference. So yeah, this is the high level overview of the idea. Okay, so now we'll discuss the implementation. So yeah, the implementation will basically be something like this. Okay, so the let me just tell you like a slightly easier way to understand how I'm going to implement it. So what I'm going to say is all the characters of set S will be in an unordered set. Okay, unordered set just to save time. So all characters of S, all characters of S, I'll put in an unordered set. Okay, so these will be the characters which are remaining. These will be the characters which are unused so far. Right. So for example, if the string was hello, I put in unordered set, so it become like ELLHO, right? That will be in the set. So now what we can try first point of difference as first position. In our set, we have the values. Actually, not in unordered set. We can put in a normal set. So it will be easy to do lower bound. Okay. So we have this in a set. We have this in a set, right? And then here, let's say the character was equal to M. Okay, the character over here was M. So let's say we want to try the first position as the first point of difference. So what we will do is we can do a upper bound, right? So set has the function upper bound. So we can call upper bound and we can find the upper bound of M, right? And as you can see, upper bound of M is O. So we can say that, okay, the first position will be O. And then the remaining positions we can fill up as, we desire in sorted order, right? So this will become a possible solution, right? So this will be we can push to a solution array. Fine, we can push to a solution array. That the string is OEHLL. Fine. Now let's say if we don't want this to be the first point of difference, right? If we don't want this to be the first point of difference, let's say here instead of M, the character was, uh, let's say the character was H. Okay, we had H over here, and we say, okay, we already tried first point of difference. We stored that in a string. Now we will try putting H over here, which is an equal value, right? We put H over here, and we said, okay, now the second position is the first point of difference. Obviously, since we already put H, we can remove it from the set. And now we say that, okay, this is the first point of difference. So let's say here it was written as, here the character was E. Oh, sorry, here the character was O. Fine. So now what we can say is, okay, first we can try making this the first point of difference. We see that it's not possible to make it the first point of difference because there's nothing larger than O, right? We do upper bound, it does not find anything. So there is no option. And what we say is, okay, let's make this equal and let's move to the next step. Okay, so we move this to the next step. And now we say, let this be the first point of difference. Now we say, let this be the first point of difference. Okay. And let's say over here it was given as E. Here it was E. So now if this is the first point of difference, what we can do is we can put L over here. We can put L over here, and then this becomes the first point of difference. Right? We put L over here, so this becomes the first point of difference. And we can store that as a possible answer string, right? So one answer string we get as HOL, and then the remaining elements in sorted order. So HOLEL is one possible answer, right? And so on, we try every position as first point of difference one by one. Okay, that's basically what we're doing. So let me write a pseudocode for this. Okay, let me write a pseudocode for this. Basically, so make a set S, which will equal to, or maybe let's call it set itself, set ST, which is equal to, or we'll call it multi-set, right? We need multiple elements. So multi-set ST, which is going to be all characters in string S. Okay, in string S. Now for I, so also we'll have a vector of answers. Okay, so possible answers will be an empty vector in the start. Okay, so for I equals 0 to I less than n, I plus plus. First, we will try making this a first point of difference. Okay, so making this first point of difference. All right. So what we will say is we will find some upper bound in the set. So we will say that set dot upper bound for the given target, which is going to be T of I, right? We're going to find this T of I. Then also we'll have a prefix so far, right? So the prefix of all the elements added so far. So what we can say is now we can have a possible answer. So possible answer is equal to this prefix so far of all the elements which are matching plus this element which we have changed so that is just greater. So plus this element. So let's call it x plus remaining elements in sorted order, right? Remaining characters in sorted string, right? In a sorted string, substring, right? So this is going to be the prefix substring plus the point of difference, which is x, plus the remaining characters. So this is one possible answer. And we can push this to our answer array, right? Answer array dot push back the string of possible answer. Okay, possible answer. Now what we can do? So once we have already pushed this possible answer back, now we can make one step front. We can say that, okay, let these two match. So if set dot find this current character, so T of I, then we can say that, yeah, these two are matching. So we can say that, okay, we'll add this value to the prefix plus equal to T of I, and we can erase this element, one element from the set. So set dot erase, set dot find T of I. Okay. And if this element is not there, then we cannot have a matching at this point. So we can just break it, right? So this is the overall pseudocode. Let's go through it again. Basically, we have a multi-set, which is going to be all the characters in the string S. We have a list of possible answers and we have a prefix. And then we'll try to make this the first point of difference. We'll find the upper bound. So whichever the larger character is, we'll put it in the position. So we have a prefix plus this just larger character plus remaining characters in sorted order. And We will push this possible answer to the answer array. Okay. If this upper bound does not exist, then we don't need to do this. We can just continue this part. Okay. Then we will say, okay, let's match this character. So we will add this to the prefix, erase this from our set, and we go to the next part of the loop. Otherwise, if this does not match, then we can just break out of the loop. So this is the whole idea. And the time complexity for this will be big O of n times, I think, n log n, because we are going to create a whole string over here and we're going to use multiset. So the time complexity will be big O of n times n log n. So the overall time complexity should be big O of n square log n. Okay. So that's the idea for this question. Let's have a look at the code. I hope it's understandable. Anyways, so basically, n is the size of our string. This is the multiset of the characters. So multiset characters, and we're going to insert all the characters in it. Fine. Now we have a string of possible answers as well as a prefix string. And what we can say is for each position, we're going to find the upper bound for this current position, right? So T of I, target of I is upper bound in the remaining characters. And we'll say that if this upper bound exists, then we're going to add this new temporary value to the answer. So basically we'll find this target value. So we're taking this gives us a pointer, right? So we'll get the value at this character. We'll create a temporary string which is equal to prefix plus this character value, prefix plus this value, plus for all the remaining characters, we're going to push them back in sorted order, right? So temp dot pushback x in sorted order. Set is always sorted, so they already get pushed in sorted order. And then we can say that this is a possible answer. So we push this as a possible answer. Okay. So this pushes all the remaining characters and this pushes it to the possible answer in the answer array. Fine. And then once we are done, we have said that, okay, now let's look for a first point of difference later on. So what we'll say is we'll try to match these characters first. So if this current character can be matched, if it's there in the set, then we will push it back to the prefix and we will erase it from the set. Otherwise, if it cannot be matched, we can just break it. Right, so one by one we match characters. First we try to match it to some largest character, and once we have done that, we try to match it to equal character and then go to the next character. That's all is basically the idea. And then if there is no answer, so if all the answers are, if the answer array is empty, we can return this. Otherwise, we can just return the minimum element of your answer. So we just return the minimum lexicographic element in our answer array. Right? So it's kind of a brute force with some optimization. We're finding all the possible strings from each least point of difference which can be found and taking minimum of them. Fine. Makes sense? Cool. Thanks. So let's move on to problem D now. I think if there's any doubt, just put it in the chat. Should we move on to D, guys? A lot of people said C was not that easy, right? So hope it's understandable now. Okay, let's move on to problem D. Problem D is also just a harder version of problem B, but yeah, it will require some prior knowledge. Okay, usually problem D requires some of the other prior knowledge. Fine. So for problem D, it's this similar to problem B, longest balance subarray. It's called balanced if the number of distinct evens is equal to the number of distinct odds. We need to find the length of the longest balance subarray. So it's the same question. Only thing is n goes up to 10 power 5 this time, and nums also goes up to 10 power 5. So we need a big O of n or n log n solution. Fine. We cannot do an n squared n cube solution like last time. Last time we could do an n squared solution, right? So here n goes up to 10 power 5. So we need an n log n solution somehow. Okay, so problem D. So basically, we need a time complexity of big O of n log n or less, and we need to find the longest balance subarray, right? And on first glance, this seems pretty impossible, right? Pretty decently hard question, I would say at least 2000. But yeah, so here are some prerequisites you need to know because I will not be explaining them right now. So prerequisite for this question, or at least my way of solving this question, is to understand. Obviously, most of you will know prefix sums, so I won't tell that. But you need to know segment trees. Okay, segment trees. The updates in segment trees. Okay, lazy updates. Even if you don't know the theory behind it, you need to at least know that this exists and how it works. Okay. So lazy segment trees for some operation. Okay. And lazy updates means it can do range queries, right? So range sum we can do, range queries we can do. Okay, so these two things you need to know. If you don't know this, this is there in TLE level 4. And also if you're, I would say if you're below specialist or expert on code forces, there's no time, you should not focus on these kinds of advanced data structures yet. You should first build your intuition. I solved in contest. No, I did not solve in contest. I actually was sleeping. Meta Hacker Cup ended at like one something, right? So I couldn't wake up on time for today's contest. I solved a bit afterwards. I mean, I started half an hour late, so I just did from a different account. And yeah, I didn't even submit till the contest was over. Like a lot of questions. I know secretary. Okay. So you're not able to understand this segmentary code? Which, what do you mean this? You're talking about the code which I wrote? Or for this question you're not able to understand? Because I didn't discuss the code yet. We'll get into the thing. Yeah. Okay. So just a brief overview of what segmentary does. Basically, what it does is, given a range, okay, just believe me that given a range, if you have a segmentary data structure, one thing you can do is you can find the sum of all elements in the range if you want. You can also add some value to each element in this range. Okay, so if this array has some values like um, 5, 7, 10, 3, 4, right? And you say that, okay, in this range to this range, you add the value 1. So it will happen in such a way that 1 will get added kind of to all these values. Okay, and this will happen in log n. Okay, this will somehow happen in log n, even though we're adding to a lot of elements. Fine. For our purposes, it's going to happen in log n. So that's the updates which we are doing. Update will be range sum. Okay, range sum. And the time complexity which a segment tree takes for this is log n. Okay, and the queries which we have is range max and range min. Okay, so a segment tree can do different updates and different queries as well. So that is possible. So what we'll do is our queries will be range max and range min. Okay, so what we can say is to the segment tree, give me the range maximum of this range, give me the range minimum of this range, and we will get our answer in big of log n or big of 1 also sometimes if the range is exactly overlapping. But yeah, we'll get our answer in big of log n to find range max and range min. For at study, it's not something to stress over, okay? Because I have had practice for almost 2 years, like serious practice. So yeah, it takes time, and practice. That's all. There's nothing. There's no secret. If you just practice correctly and practice consistently, you will be able to think more and think longer about these types of questions. Okay, so update is our range sums, and our queries are going to be range max and range min. Okay, so how do we solve this? Um, yeah, so how do we use this idea? So this is our prerequisite. Let's get into the actual question. So in the question, it says that it should be balanced, right? So I'm going to give you some like statements. You'll have to follow it because giving an intuition, honestly, I'm not sure how to exactly give the intuition, but I think it should become evident. So basically, what we're going to say is that if some value, okay, if some subarray is balanced, okay, if some subarray is balanced, let's say this subarray which starts at this L and ends at this R, okay, starts at an L and ends at an R is balanced, then what we can say is the number of distinct odd numbers and the number of distinct even numbers in this range should be equal, right? So distinct odd is equal to distinct even. Okay, so okay, I'll try to give the intuition actually. So this will call intuition, right? And then one thing you could think of is, okay, what if we had prefix sums on distinct numbers? Okay, we had prefix sums on the distinct numbers. For example, 7 appears here, 9 appears here, 2 and then 2, 3, 7, 5. 2, 1, 0, 1, 3, something like this. These are the numbers. Okay. So then from 0 to n, we will count the distinct numbers. Okay. Distinct odd and distinct even. So we'll that, okay, say distinct odd number. So the odd number is increased by 1 and even number so far is 0. Then here odd number has increased again. Even number so far is 0. Let me just write in some other color because it's not very clear. Let's say that here, since there's a 7, so we can say that, okay, the number of distinct even numbers is 0. Number of distinct odd numbers is 1 so far. Then over here, number of distinct even numbers is 0. Odd numbers is 2. Here, number of distinct even numbers is 1. Odd numbers is still 2 so far, right? We're taking prefix. So we're taking prefix. And then here, distinct even numbers remains 1. Odd numbers remains 2. Then here, distinct odd numbers becomes 3. Even numbers remains 1. And then here again, here this odd numbers also still remains 3. Even numbers becomes 1. Remains 1. And then here number of distinct odd numbers becomes 4 and even numbers becomes 1. Right? So this is the prefix sum, the prefix distinct numbers which we are counting. But the thing is we cannot find the distinct numbers in LNR using this approach. We can't find distinct even numbers in this range. For example, even numbers in this range by this method. And the reason is that, or distinct odd numbers, even or odd numbers in this range by this method. And the reason is that, for example, 7 appears here for the first time in this subarray, right? 7 appears here for the first time in this subarray. But because 7 had already appeared here, it is not being counted, right? The number has not increased. So we can't just do prefix count of distinct numbers, right? Does it make sense? How many problems did I solve in Hacker Cup? I solved all the problems. I think. I'm not sure about the last one. It might be VA. I'm not sure. But ideally, I think I solved all the problems. Is it possible to use this solve this using DP? I don't think so. Like, I'm not sure. I can't see a way to solve this with DP. I don't see a way to do it without some kind of range query data structure. But there might be some method. I'm not fully sure. Anyways, so let's get back into it. So how do I? Okay. So then if I cannot use prefix sums, how do I check if it's balanced? Okay. How do I check for balance? And basically the idea is that when we fix our L, okay, when the L value is fixed, let's say L equals 0, then we can use the prefix count of balance to keep track. Okay. So let me just define it like this. Balance is going to be the number of distinct odd numbers so far, minus number of distinct even numbers so far. Okay, number of distinct even numbers so far. Right. So every time I see an odd number, new odd number, it will be +1. New even number, it will be -1. Right. So every point which has a 0, that point will be balanced. Okay. If every time I see an odd number, I add +1, and every time I see an even number, I add -1. So let's say let me just write some random numbers so that it becomes clear. Okay, so what is my values of balance? Okay, so let me just define my values of balance. So at the very start, my value of balance will be 1. Okay, because I saw just a new odd number. Now I'm going to see a new even number for the first time, so I -1 and 0, right? And then I see the same even number, so I don't change. I see the same odd number, so I don't change. Now I see a new even number, so I do -1. I see another new even number, so another -1. And I see a new odd number, so +1, and it becomes this. Now I see an old even number, so no change, right? So it's not distinct, so no change over here. So -1, -1, -1. 4 is finally a new even number, so another new even number, -2. And then 6 is another new even number, so -3. 8 I've already seen before, so sorry, 6 is not new. 6 is also I've already seen before, so it remains -2 itself. It remains -2, remains -2, remains -2, right? Or for example, let's just keep two new odd numbers here, for example. So let's just say 13 and 15, okay? So these are the two numbers which I'm going to put here. And then we can say that, oh, 13 is a new odd number. So I do a +1 and this will become -1 at this position and this will become 0, right? So now every position which is 0, every position for which is a 0 is a valid position, okay? So convince yourself that starting at L equals 0, starting at L equals 0, every every R value such that balance of R is 0, then the array L to R, the subarray L to R is balanced. Okay. And that is very obvious because we're just doing number of odd numbers minus even numbers. If odd is equal to even, then it will be 0 at that point, right? So that's all I'm trying to say is that if you take, let's say at this position it's a 0, right? So if you take all these elements, it's going to be balanced because distinct odd numbers is 1, distinct even numbers is 1. 1 minus 1, 0. Similarly, if you take this position, this whole thing also will be balanced because you can say that distinct odd numbers and even numbers are equal since odd minus even is equal to 0. Okay, odd minus even count is equal to 0. Fine. So are you guys following this much? Can someone just put in the chat that you understood what balance means? How I've defined this balance or this prefix sum? It's basically a prefix sum of odd and even distinct numbers. Okay. Yeah. Okay. Good. So you have understood what this balance means. So now what happens if, okay, so what I can say is the last 0 which occurs in my array, the last 0 which occurs in my array, that is going to be the longest balanced subarray starting at this L. Okay. So starting at given L, starting, let me just write it a bit neatly. Actually, okay. Starting at the given L, and starting at the given L, the longest balanced subarray will be from L to the position of the last 0. Okay, from L to the position of the last occurring 0, of the last 0. Fine. So this is going to be our balanced one. So here in this subarray with this L, as you can see that this is the last occurring position. Okay. Now, what if we increase L? Okay, what if we increase L? What happens if we increase L? Okay, if we increase L, fine. What it means to increase L is basically our L pointer says that this is the starting point, right? But what happens if we increase L and we say that okay, let us remove this element, let us remove the first element. Let's say L was equal to 1. Okay, L was equal to 1. Then what is the new balance array? Okay, what is the new balance array? And as you see, the new what happens to the new balance array is that so basically this 7 was never seen. Okay, this 7 was never seen, and we're basically starting off at 8. Now 8 is a distinct even number, so at this position becomes -1. Again, 8 is a distinct. Now this 8 is not distinct, so it remains -1. And then the 7 is a distinct odd number, so it becomes 0. Then after this, 6 is the distinct even number, so it becomes -1, -2, -1, like this. Okay. So this is the new updated balance array when we have removed the first character. Okay, when we have removed the first number. Now, as you can see, most of this array is the same. The only part which the change happened was this 7 got removed, right? So the next time the 7 occurs will be at this position, right? The next time the 7 occurs will be at this position. So everything from this point onwards will remain the same. Okay, everything from this point onwards will remain the same because then the distinct 7 was removed from this point and the next point the 7 occurs is there. So everything from that point onwards will remain the same, right? And what has been affected? It has been affected is this range, right? Because now this odd number is not there. This whole range has been subtracted by 1. Okay, so balance of this range has been subtracted by 1 basically, right? So all the values in this range have been subtracted by 1. This 0 became -1, this 0 became -1, right? So I hope you're understanding how this is giving us segment tree ideas. Yeah, I gave Hacker Cup round 1, guys. Pretty fun contest, but I heard a lot of people were getting issues as well. I think someone will cover it, I guess. I'm not sure if there'll be a PCD for it because usually there isn't, but I guess because I think there might be a PCD for it, like recording, maybe today or tomorrow. I'm not sure. Anyways, um, I hope I will get D because I'm not sure about my D solve, but other solves were pretty fine. Anyways, going back to the question, are you guys able to see why there's a segment tree? So when we remove the 7, then the next 7 is going to be from the next 7 onwards, the array will be unchanged. But then this whole array till that point will become -1. Okay. So let me give you another example. Let me say next we increase our L again and we go to L equals 2. Fine. We go to L equals 2. Then this 8 also gets removed. This doesn't affect anything. Only this range. There's no range to do put -1 on. So this does not affect anything. Fine. So now we'll remove this 8 as well. Right. We remove this 8 as well. So now what happens? This position. So the next time an 8 occurs is over here, right? Next time an 8 occurs is over here. So the values beyond this point do not change, right? The values beyond this point do not change. But because we removed an 8, all the values in this range, all the values which are there in this range, they get added with +1. Okay, they get added with +1 because now there's a even number which has not appeared. So basically the -1 effect is removed. So all this whole range will get a +1, right? So this will become 1. This will become 0. Sorry, this will become 1. Yeah, this will become 0. This is going to become -1. This is going to become 0 again, so on. Are you getting me? So basically the segment tree can handle like a +1 -1 operation over a range, and that's going to keep our balance array in sync, right? As we increase L, as we increase L, the removed element, the removed A of L, right? We can find the next occurrence of A of L using some map or something. So next occurrence of A of L, right? Next occurrence of A of L, right? Up to, so starting at the current position, so from the leftmost position, which is let's say I or L, right? So from the leftmost position L to the next occurrence of this A of L -1, what we do is we add a +1 or -1, depending on whether it's even or odd, using the segment tree. Okay, so that way we are keeping the balance array, computed correctly, even in n log n, right? We're keeping the balance array computed correctly, even in n log n. Fine. So we are ensuring that when we increase L, when we increase L, the balance array is corrected. The balance array is correct in big O of L itself using the range query of our segment tree. Okay, so if the balance array is stored as a segment tree, it will be kept as a range query. Can you share the solutions of yesterday? Thing is, they'll make the scoreboard public in some time, right? It's not public for anyone. Like even I can't download the solutions. So I think it's because they were having some issues during the contest, right? That's why they're doing like some clarifications and that stuff. So once that's over, they'll make it public. It's fine. Don't worry about it. Anyways, so let's go back to the question. We are ensuring that the balance is correct in big O of log n. And now the only thing we need to know for each position L, right? Once the balance array is there, for each L, we need the rightmost position, which is a 0. Okay, rightmost position, which is a 0. Okay, which is a 0. And we can do this also with the segment tree itself. what we can do is basically we can say that um, when we have the secretary, right, and the secretary looks something like this on our array, right, and what we can say is that we can store the max and min of each range. Okay, max and min value in each range, Okay, so what will this max and min help us? So let's say the max of this range was like 2, then and the min of this range was -1. Okay, then obviously to become from 2 to -1 you would have gone to 2, 1, 0, -1, so on, right? So basically if max is greater than equal to 0 and min is less than equal to 0, then that means that this half of the segment tree has a 0, correct? If the max of this half is greater than equal to 0 and min is less than equal to 0, that means that going right in the segment tree will means that there is a 0 to the right if we go down the segment tree. And then otherwise we will go down the left of the segment tree, right? Because we want the rightmost position. So basically what we'll say is that maintain min and max in the segment tree, right? Maintain min and max of range, min and max of range in seg tree, right? In seg tree. Then we're going to have this thing. We're basically going to say, if okay, start at root, start at root, start at root. Then we will say, we'll say that try to go to the left child or right child, right? So if right child dot min is less than equal to 0, is less than equal to right child dot max. Okay, right child dot max. Then we can go to the right child, go to right child, right? Else we can go to the left child. Okay, go to the left child. So this is like a custom segment tree. We'll have to implement this kind of a thing ourselves to find the rightmost 0. So if the right child dot min is less than equal to 0 and less than equal to right child dot max, we go to the right child or the left child. If we are at a single node, obviously we can just return the position. If we are at a leaf node, just return the position, right? And if ever it goes out of range, right? If it goes out of range, for example, if um like left is greater than 0 or right is become less than 0, that means we have completely gone out of range. So we can return -1, right? That means that there is no zeros. So we can just return -1. So this kind of recursion starting at the root of the segment tree, it's going to find us the rightmost 0 in the segment tree, right? It's going to find us the rightmost 0 in the segment tree. Basically, we're saying if the max and min have a 0 in between, that means that 0 must have occurred, right? The 0 must have occurred in the array, and we can go down the array. And this technique only works because um, these elements in the prefix sum also, they are all doing ±1, right? So for example, if you have a prefix sum of balance which is 2, then it can't become 10, right? It will only become like 2, 3, 4, 5, then 10. So similarly, if you have a max of 2 and a min of 5, -5, then it will become 2, 1, -0, -1, -2, so on till it becomes -5, right? So the 0 comes in between. And that's why this technique is working on the segment tree. Basically, we're just going down the segment tree to whichever side has a towards the right side if it has a 0. Otherwise, we'll go to the left side if it has a 0. If neither of the side have 0, then we can just exit. We can say -1. Right, and this is how we're finding the rightmost 0 in a segment tree. Did you find D easier than C or B2? No, I did not find D easier than C or B2. Wait, no, D was like I'm not actually sure actually because D I'm not sure about my answer. So we're talking about Hacker Cup, right? So D I'm not sure about my answer. Like I had a intuition, I coded it, I could not prove my intuition. So that's why I would not say it's easier. But yeah, I got the idea pretty quickly. I got the idea in like 10 minutes, but I was not able to prove it. When there was like 5 minutes remaining, I just coded it up and submitted it because I had nothing better to do. But B2 was very logical, C was also fairly logical. So yeah, that's how it was for Hacker Cup. Anyways, so let me just summarize. So we're going to create a balance array, right? Summary. Okay, so first summary, we have a segment tree, seg tree with range sum update and which stores range min and range max for each node. Okay, range min and range max for each node. Range min and range max for each node. Okay, max for each node. Now, what we're going to do is we're going to start at a node. Sorry. Now what we're going to do is we're going to create the balance for L equals 0. For L equals 0, create balance array, right? Balance array as I defined before, and store in the secretary, right? So make a secretary and make it into a secretary. Depending on how your secretary template is, you can do that. Make it a secretary, right? And then what we're going to do is, we're going to say, obviously answer will be the rightmost zero in the secretary. So rightmost zero in the secretary plus one in the start. This will be our answer. Then for each L from 1 to L less than n, right? L plus plus. So we're moving the left pointer. And what we'll say is we have to remove the a L minus 1 element from the secretary, right? We have to remove this number from the secretary. So what we can do is we can find the next time it occurs. So we'll say that. So yeah, we have to pre-compute a map for whenever each element appears the next time. So we can say that secretary dot range sum, right? Range sum update. And what will be sum? We can add plus or minus 1. We can add it from this left point. So from this left point till the right point will be the next occurrence of AL minus 1, right? So next occurrence of AL minus 1, right? So whenever this character appears the next time, that position we have to do range sum of plus minus 1 based on whether it's odd or even. Okay. And then we just need to find the rightmost zero again, right? Rightmost zero in the secretary. So that will be like a function inside the secretary itself, like I described. So rightmost zero of the secretary minus L plus 1, right? So R minus L plus 1. This is going to be a rightmost point. This is going to be L point plus 1. And our answer will be like answer equals to max of answer in this. Fine. Answer is equal to max of answer in this in our loop. So for every L value, we are finding the corresponding rightmost zero. Once we have found the rightmost zero, we will update our answer. And finally, we can print the minimum, find the maximum length, right? So print return answer, sorry, once this whole loop is done. Fine. So this is going to be the general summary of what we're doing. And yeah, we need to use the map to keep next occurrence of every element. So that also we need to pre-process. Okay. Let's get into the code. The time complexity of this is just n log n, since uh, each operation of the segment tree is just log n, right? So range sum is log n, and finding the rightmost zero is also log n. We're just traversing down the nodes. So yeah, the whole time complexity will be n log n itself. So let's have a look at the code for this. Okay. So first, this whole class is my segment tree, right? This is a segment tree template which I found. Um, there's nothing much. It's just it stores minimum, maximum, and lazy. Okay. So minimum, maximum, and lazy, and it just builds the segment tree. So if you want, you can go through the code when it gets added to the description later. But it's just a normal segment tree for lazy updates, which stores minimum and maximum. Okay. So that you can find anywhere on the internet. The only new thing in this is find rightmost zero, right? So this is a new thing, find rightmost zero function, and it does exactly what I described. Basically, it says that um, if the current value is minimum is greater than zero, or if the current range maximum is less than zero, obviously it's not in range, so return -1. If it's a leaf node, then we can just return the position. And this value, this is push is there just to update the lazy, right? So if it was a lazy node, it's just going to make sure that the lazy update happens. So don't pay much attention. This push is just to do the lazy update. So now what it's going to do is it's going to try first the right half. It's trying to go down the right half. If going down the right half gives us a -1, then it's going to try going down the left half. Fine, and it's going to try to find rightmost zero on either side. So this way we can use our segment tree structure to find the rightmost zero occurring in our segment tree, right? So this is a kind of common idea, like find the rightmost zero in a segment tree, find the smallest number in the segment tree, etc., like all these kinds of problems. Yeah, I think the final scoreboard should change because even I'm not sure if my D was correct, and I think a lot of people, at least on Codeforce's comments, I saw a lot of people who solved D and their solutions were incorrect. So yeah, it might change. Anyways, back to our question. So this is the segment tree. Now, for each number, we need the next occurrence, right? So here I just make a map and I have a vector which is basically like when is the next occurrence of a given value. So I'm just using this map and finding that pretty basic logic, right? For each element, you just need to know where it next occurs. So you go through the array in reverse and you find it. So that's all. And now I'm going to do the balance calculation or the prefix sum calculation. Here I just call it P for prefix. And for each element, if it's an odd element and it's unique, I do plus plus. And if it's an even element and unique, I do minus minus. And then the value of gets set. Fine. Now here I define my segment tree on my array P, right? On my balance array, I find my segment tree. My initial answer will be from L equals 0 to the rightmost 0. So that's why it's rightmost 0 minus L, which is 0 plus 1, right? So this is my initial answer. Now for each I or each L from 1 to N, I will remove the previous L, right? So nums I minus 1, I'm going to remove from my structure. So basically what I can say is, so I need to remove from 0 to R, right? I can do subtraction operation or addition operation on my segment tree with the value. So if it's an odd number, I will do minus 1. If it's an even number, I'll do plus 1, right? Because I'm removing it. Because here odd was plus 1, even was minus 1. So to remove it, odd will be minus 1, even will be plus 1. So in this range, I do range addition or range subtraction. And then finally, for the final answer, it's just max of the answer and find rightmost 0 minus I plus 1. So whichever the rightmost 0 is, still the current L and plus 1. And finally, when this whole loop is done, I return the answer. So yeah, it's a bit on the harder side. I would say it's easily like 1800 to 2000 problem plus, right? Easily on code forces. So yeah, decent problem it was. But if you're familiar with segment tree, if you're familiar with these tricks, it's not that hard. All right then, guys, that's it for today's problems. Any doubts, you can go ahead and ask me. Can I tell my lead code rating? I have not done much lead code actually, so I'm not sure if it reflects my current like true rating, but I think my current rating is like 2300, right? But yeah, I've not done that much lead code. I think if I do like more contests, it should probably increase. But yeah, that's my current rating. All right then, guys. Um, any doubts, you can go ahead and ask now. This is my profile if you want to see it. And if you want to see the submissions, they're here. So you can go check them out as well. All right, guys, then. I don't see much doubts. So let's end the stream now. Just a reminder to check out the Eliminators course, guys. We do put a lot of effort into that. And like, if you think about it, all of us are like high rated coders, right? So it's basically our like form of contribution to the CP community to make those courses. So yeah, and they're like super affordable as well. So I hope it's useful for you guys. Ratings of problems for yesterday's contest. You mean Hacker Cup? Okay, let's think about it. Um, okay, so I guess the first one was pretty simple. Maybe like 800 for the first one, right? On CF. Wait, wouldn't it be on C list, to be honest? Wouldn't it be on C list? And the second one, yeah, second one was nice. So maybe 1300-ish. Third one was again like 800,000 at most, right? It was pretty simple. Observation. Fourth one I would say was pretty hard. Like if you're not good at number theory, the code was pretty long. I remember it. I remember my code being pretty long for this one. Yeah, quite long. So the implementation was a bit heavy. So I would say the fourth one would be like at least 1600, 1700 plus, maybe 18, 1900 also. The fifth one was easy for me. I don't know. I found it easy. Fifth one, I would say 1600, and last one also 1800-ish. Like the last three can be anywhere between 1600 to 1800, 1900. That's what I felt. If there was a presentation error, it won't be judged. I'm sorry. I think most probably presentation error means that either you did a wrong answer, or like, see, sometimes even for wrong answer it shows presentation error, so you can't trust it. Either you did a wrong answer or you printed some extra character or something like that. So either way, I don't think it will be judged if there's a presentation error. Anyways, do they have Hacker Cup on here? Yeah, they have not put the rating yet. Cool. Anyways, guys, I think that brings us to the end of today's session. A1, A2, B1 would take you to round two. I guess maybe, I'm not sure actually. Uh, See, the scoreboard has not settled yet, right? A lot of people will like the system testing is not even done, right? Only like 10 test cases were tested. So a lot of people will have bugs and they'll get removed. So once that all of that is done, then only we can say, right, how much will get you selected. But up to 5,000 works, right? Up to 5,000 rank. So let's do it at 5,000. 490 for what is the 5,000th rank? Yeah, I guess A1, A2, B1 in like 1 hour would definitely get you within 5,000, right? From what you can see here. So yeah, for Arpan. All right then, guys. Thank you for watching. See you in the next PCD, right? Uh, Hope you learned something. Do upsolve the ones which you haven't solved in the contest, right? This contest was a bit implementation-y, but yeah, do upsolve it. Thank you and see you next time. Bye bye.